Maybe the first question to you: how do you see the life sciences in your area of research, and what are major developments, new developments, which made your work at the end possible?
I'm working mainly, as my professor title already saying, working in metabolomics, one of the new omics fields in life science. I think there are kind of really have been made significant advancements in the last years on the genomics side and also metabolomics side. So I'm personally specialized on spatial metabolomics, so an imaging technique to see metabolites in systems, but I also see major advancement in life science for microscopy. So we need to observe first to kind of understand our systems, host microbe interactions, so microbial cells within host tissues. So I see, or also life science will advance a lot because we have these new omics techniques available.
So the techniques allow now a new view, open a window to something. Maybe you explain a bit to us what can we see now, what we couldn't see before these developments, these technologies were developed. Means what were challenges which now maybe can be overcome.
So we had big challenges in, I think, all the omics and especially in metabolomics. It was very difficult to measure metabolites in a comprehensive way, and big advancements were done. So we can now from tissue samples measure all the metabolites present, including also peptides and other things. And still, there was this one big challenge to say from which cell and which organism kind of in host microbe interactions, spatial metabolomics, like a microscope which can observe chemical compounds. We can do this on a single cell level and can look into a sample and have, like on a microscopy slide, we can visualize where specific metabolites are coming from. So that is really a big advantage that we now can see all the building blocks of biochemical building blocks, see their places and also the paths they are taking. And that will give us major insights in future. I'm pretty convinced about that.
There is this kind of research priority area, key life sciences, where you are now part of, and hopefully also participating in shaping that research area. What makes KLS so special for you?
I think it gives us a platform for all faculties and researchers from very different disciplines to come together, like with workshops and seminars, and kind of exchange via one talk where you maybe are not so familiar with. You bring together a clinical scientist, a plant physiologist, and a biochemist like me, and you start to talk about the problems I really like and look forward to kind of immerse myself into this field. To also, like, a big topic is evolution, talk about those experts and see how methods and kind of thinking can be applied to metabolomics research from an evolutionary perspective.
Life science offer you all what you need, or is there some components, elements missing which you may think of asking or helping in complementing, or you would leave it?
I will build up the metabolomics platform, which will be open for KLS members, and we can. That's my kind of plan of future, so that there will be, for example, what I talked about, this spatial metabolomics method available. That's something I will build up for KLS, and so far I can't say there's something missing. Of course, there's a big part of my research is methods driven, and for doing those methods, you need the devices. So that's something we right now try to get established with a Großgeräteantrag.
Could you share with us some ideas and some views on your own research, which you want now to develop and continue to do in the next few years here in Kiel?
The first thing is always you need the right methods and procedures in hand. So we will develop more and better methods to do very high spatial metabolomics method, combine this with other omics. But then in terms of questions we want to tackle, we want to use those methods to look also into very specific, into the interactions of host microbes. Specifically, I will focus on different gut systems. So from mice to the human system, to really look into kind of the co-metabolism of host and microbes. I think there are some very interesting model systems here around, which I can kind of join in and bring in this metabolic view into the system. And I'm excited to explore that area where we really can say, okay, this is a healthy environment, and this is an environment, a gut environment where things go wrong. And we will focus on a few compound classes, molecules. And for me, this first contact point is important. I think where cells collide and come together, these are the membranes. So we will focus on membrane lipids, specifically steroids. This is an exciting research area I kind of brought from my times at the MPI. So we will look at steroids. And also we want to look into glycans, because I think glycans have this unique fingerprint of kind of recognition, maybe sometimes defense. And I think visualizing those compounds in interactions, in cell interactions, will be quite interesting for us. And this is like this a few years in future that we can show those compound classes in biological systems and have this available for kind of the toolbox in life sciences, which is not yet possible. So this is an advancement we can only do with a combination of certain technical devices we want to have in Kiel, plus the expertise and the model systems.
Where will the life sciences be in 5 years or in 10 years? What will be solved? What will be not yet solved? Where are windows which just wait to be opened and may be opened by you?
I think what's interesting right now, and that's why I think it's difficult, is that the life science has in a tremendous speed at the moment. There are new methods coming up from all areas, like CRISPR-Cas. We have very super high resolution microscopes where we now start to see things which we have never seen before. And that kind of speed will also shape the future. And I think we still observe a lot. We do describe systems with all the omics we have available, but I think the future will really will be the integration of the data. And I think maybe with the help of AI, for example, I'm not an expert in this, but I think there are people out there which can combine, let's say, metabolomics data with imaging, with genomics data, and maybe I don't know, some histology or some detailed other fluorescence microscopy data, and kind of can give us new hypotheses which we can start to kind of look into and kind of find new ways. I think that integration and bring together, I think we need this common ground, and that the biologist can talk to a chemist, can talk to a computational biologist or a mathematician, bring this together, having this I think that will come because each part of life science kind of extends into the other fields. So in terms of the interactions between microbes and hosts, where it's a specific one, I think we will more and more see what big role the microbes really play in kind of the interactions with eukaryotic hosts, etc. People observe, they bring the data, they have lots of sequencing data, but they are now at the step to develop it into a metabolic model, or then up to us presenting, showing where specific metabolites are. And that's the next step and next phase in life science, to combine all those things.